and they penetrate over 1,000,000 kilometers through the solar wind. We know the properties, the density and speed of the solar wind, so we can figure out that for a natural comet, with the characteristic outflow speed of these jets that come off pockets of ice on a natural comet.
One way out of this dilemma of why is it so big is if it was targeting the inner solar system by design. And indeed, the trajectory is aligned with the plane of the planets around the sun to within 5 degrees. The chance for that at random is 1 in 500, okay? And it's moving in a retrograde trajectory opposite to the motion of the planets, which is ideal for it to release mini probes that will get into the planets. It gets close to Mars, it gets close to Jupiter, it goes on the opposite side of the sun relative to Earth when it's closest to the sun. And that's the time when a spacecraft could do a maneuver to take advantage of the sun's gravitational assist.
At 0314 UTC on December 2nd, the automated survey telescope at Cerro Tololo detected a fast-moving object less than 1 arc-minute away from 3IATLAS's projected light path. The system flagged it as a potential error, a ghost reflection or background noise from a hot pixel. But within 17 minutes, a second observatory in La Palma confirmed the same coordinates. A third confirmation from the Korean Bohyunsan Optical Astronomy Observatory locked it in. It was real. The object was small, barely brighter than magnitude 17, and nearly invisible to non-specialized scopes. But it had all the hallmarks of a fast inbound trajectory. What made this so unusual was the timing. Just as 3IATLAS began entering its most observable window near perihelion, this second object appeared out of the glare. It had never been seen before, not in any archived wide-angle scans, not in deep-field composite data, and not even in solar and heliospheric observatory (SOHO) data. Its initial velocity was clocked at over 45 kilometers per second, nearly identical to 3IATLAS. Early astrometry suggested a shared inclination, 27.1 degrees off the ecliptic. These aren't random numbers. That level of orbital symmetry is almost unheard of for two unconnected interstellar objects. This wasn't just a close pass. This was near orbital lockstep. By ZO5 Seoul UTC, amateur networks had joined the search. Observers in Australia and southern Japan were able to stack and enhance early detections, confirming its presence with distinct infrared glow. The object had no visible tail, no outgassing signature, and yet it glowed consistently, as if illuminated from within. It wasn't rotating randomly like a typical asteroid, and it wasn't cold. By midday on Earth, tracking networks around the globe had issued alerts, and the question on everyone's mind was no longer, is this real, but why now? From the moment the orbital data was plotted, astronomers noticed something deeply unusual. The newly detected object, designated C2025X1, was not only approaching the inner solar system at the same time as 3IATLAS, it was following almost the same path. Its inclination, perihelion distance, and velocity vector mirrored 3IATLAS within just fractions of a percent. This is not typical. Most interstellar visitors, like Oumuamua or 2I Borisov, enter the solar system at wild randomized trajectories. They're unbound, uncoordinated, and exhibit no patterns relative to other known objects. But C2025X1 isn't just arriving at the same time, it's travelling in synchronized proximity to the most debated object in modern astronomy. Astrometric overlays showed a separation of just 0.09 degrees from 3IATLAS's orbital plane. In spatial terms, that's equivalent to flying two spacecraft across the solar system side by side, less than a few thousand kilometers apart. This triggered alarms in orbital dynamics teams. Was this object gravitationally bound to 3IATLAS? Was it ejected from the same origin system, or something more complex? The concept of a co-moving pair began circulating. In astrophysics, a co-moving pair refers to two celestial bodies with shared momentum, either because they form together or because one is following the other intentionally. Some began to speculate about phase-locked motion, a scenario where two objects are guided along the same solar ingress trajectory by shared origin conditions or engineered parameters. Whether natural or not, this parallel trajectory has become one of the most compelling aspects of the detection, because if it holds, we're not just dealing with a new comet, we're witnessing an event that calls into question how alone 3IATLAS really is. For weeks, a niche group of theorists and skywatchers on platforms like SpaceTracker.net and Celestial Watch have proposed a controversial theory, that 3IATLAS may not be alone. They called it the silent twin hypothesis, the idea that a second object, invisible due to viewing angles or observational blind spots, could be travelling in phase with Atlas, either as a fragmented sibling or a deliberately timed counterpart. Until now, mainstream science largely dismissed it. But C2025X1's appearance has forced that discussion into the open. The term silent twin implies more than coincidence. It suggests intentional motion, two objects moving not by chance but by synchronization. Historically, only binary stars or known multi-body gravitational systems exhibit such patterns. But this situation is different. There is no visible gravitational tether between the two, and yet their shared trajectory, acceleration, and proximity hint at some kind of linked history. Several new questions now emerge. Was this a fragmentation event, where a single larger object split long before entering our system? Or did both originate from a shared interstellar system and enter the solar corridor due to a coordinated ejection, perhaps from a collapsing planetary shell or ancient stellar event? More speculative researchers are revisiting comparisons to Oumuamua and wondering if 3IATLAS isn't just a one-off anomaly, but part of a broader class of paired interstellar visitors. The silent twin label no longer sounds fringe. With C2025X1 now confirmed, astronomers are forced to confront the possibility that we've been tracking only half the story, and the other half just revealed itself, quietly but unmistakably. One of the first red flags about C2025X1 emerged not from its brightness, but from its pattern of change. Within just 12 hours of continuous observation, astronomers noticed the light curve, the variation in its brightness over time, was unlike anything typically seen from comets or asteroids. Rather than displaying chaotic tumbling or random fluctuation, the object pulsed, every 7.4 hours, a near-identical brightness. Peak emerged, followed by a sharp, predictable drop-off. This cycle repeated itself multiple times, confirmed by telescopes across 4 continents. Such consistency points toward regulated rotation or even surface modulation, a phenomenon where reflectivity changes not because of spin alone, but because of structured surfaces or emission patterns. Natural objects rarely behave this way. Comets typically exhibit erratic light curves due to jets of gas and dust erupting in different directions. Asteroids, unless perfectly symmetrical, show asymmetric brightness shifts. But C2025X1 is steady, disciplined. Its brightness change almost resembles the turning of a smooth reflective body, like polished metal under a controlled spin. This behavior raises unsettling possibilities. If the object is rotating with such precision, what force initiated and maintains that rotation? Could it be internal mass distribution, like that of a solid core object? Or could it be something more exotic, a form of artificial stabilization? Some researchers have pointed out that satellites and probes use timed rotational pulses to orient themselves. While there is no evidence of propulsion here, the shape of the light curve has raised quiet discussion about non-natural motion characteristics. Whether it's a chunk of metallic debris from a long-lost exoplanet or something with a more advanced history, C2025X1 is behaving with a level of optical discipline that's not easy to explain and impossible to ignore. When light from the sun reflects off a surface, it carries a unique spectral signature, a chemical fingerprint that tells scientists what the object is made of. When telescopes began collecting spectra from C2025X1, the results surprised everyone. Instead of the familiar signatures of water ice, carbon compounds, or silicate dust, all common in natural comets, the spectral returns pointed to something else entirely: nickel-iron alloy with hints of vanadium and chromium. These are not common surface materials for icy, interstellar objects. In fact, they're much more consistent with core remnants of differentiated planets, objects that once underwent geological layering, where heavier elements like iron sank to the core while lighter materials floated to the surface. That suggests this object may not be a comet at all. It may be the fragment of a planetary core, stripped of its mantle and crust, exposed to the vacuum of interstellar space for millions of years, are now entering our system with an eerie metallic gleam. These kinds of M-type fragments are exceedingly rare. None have ever been confirmed among interstellar visitors, and yet here it is, right next to 3IATLAS. The implications are extraordinary. If two objects, both rich in metal, both travelling together, are entering the solar system now, it may suggest a shared violent origin, such as a planetary explosion or star system collapse. Or, more provocatively, some form of engineered ejection, where materials were deliberately flung outward. The reflectivity or albedo of the object further deepens the mystery. At over 0.6, it's brighter than most known asteroids. Combined with its size and rotation, that points to an object that's not just unusual, but unique. One of the biggest questions raised by the appearance of C2025X1 is, why didn't we see it earlier? With today's technology, automated sky surveys, deep space infrared detectors, AI-enhanced star maps, missing an object of this brightness and velocity seems unlikely. But here's the answer: geometry. Until December 1st, Earth was positioned in a way that placed C2025X1 almost directly behind the Sun's glare from our vantage point. Any object within 15 degrees of the solar disk is nearly impossible to detect using ground-based optical methods. That zone is called the solar exclusion cone, a blind spot even our best telescopes avoid, and that's where X1 was hiding. As Earth shifted just enough in its orbit, the object emerged from this glare cone and became visible. The timing is razor-thin. If 3IATLAS had not drawn attention to this region of space, it's possible this second object would have gone unnoticed until it was already outbound. What this reveals is critical. Our detection grid is not as complete as we think. There are gaps, there are blind angles, and there may be more. This also raises another concern. If these two objects are part of a convoy, a series of interstellar fragments or engineered bodies, then others may still be lurking within observational shadows. Some may still be inbound, others may have already passed. The brief delay in C2025X1's appearance wasn't due to its nature, but due to Earth's motion. We didn't see it before because we weren't ready to see it. In a rare move, NASA confirmed that the James Webb Space Telescope, JWST, is adjusting its observing schedule to track C2025X1. Normally, JWST's calendar is locked in months in advance, focusing on deep-field galaxies, stellar nurseries, and exoplanet atmospheres. But this object has triggered an override. Why? Because the data from early ground-based telescopes indicated spectral anomalies that standard Comet models cannot explain. The JWST science team saw enough evidence to justify a time-sensitive pivot, reallocating telescope time to conduct targeted infrared and mid-infrared spectroscopy on C2025X1. The goal is simple: figure out what this thing is. Infrared spectroscopy allows scientists to measure surface temperature, mineral composition, and trace volatiles. If the object contains metals, it will reflect infrared radiation in a very different pattern than ice or carbon-based dust. More importantly, JWST can detect thermal asymmetry, the difference in how heat is emitted across the object's surface. This could reveal whether it is rotating naturally or stabilized by internal structure. Instruments like MIRI, mid-infrared instrument, and NIR-SPEC, near-infrared spectrograph, will be used to scan the object across multiple wavelengths. These tools are sensitive enough to detect organic compounds, silicate grains, and even possible artificial coatings, if they exist. This decision signals how seriously the scientific community is taking the situation. Redirecting a $10 billion telescope isn't done lightly. But when a second interstellar object enters our solar system, in near formation with another, priorities shift. The observations are scheduled for December 3-7, overlapping with perihelion activity of 3IATLAS. Whatever C2025X1 is, the Webb telescope is now watching.